Okay, welcome back. So I see right off the bat we have a question in the chat window, so I guess we'll start with that. Nathan is asking, assuming that some training data is linear, is it guaranteed that Adeline will not get stuck in local optima? So the problem is that word some. To guarantee that Adeline or the perceptron for that matter will not get trapped in local optima, the concepts have to be linearly separable. That's what leads to the error surface being convex. So if it's only some, I'm interpreting that there's some that is not, which means that we can no longer guarantee linear separability. So no, you can't. If the concepts are truly linearly separable, then yes, you can guarantee that it will converge to the global optimum. However, keep in mind that that's rare. Okay, so what we're going to do today, the primary topic is logistic regression, which is another linear model. It is a very commonly used model in machine learning. And it's another one that I would put with naive Bayes to say that before you start looking at more complex models, you should probably start with either this one, logistic regression, or naive Bayes. Because even though, as I just said, a lot of concepts may not be linearly separable, you may still get sufficiently good or sufficiently strong performance that there's no real need to become much more complex. But before we jump into the discussion of logistic regression, there was a detail left over from Wednesday that I didn't get to, and so I want to kind of finish off that conversation. In particular, if you look at the gradient descent rule, and you'll recall that we said that both Adeline and the perceptron used gradient descent, even though in the case of the perceptron, the connection to gradient descent was less clear, and the way we demonstrated it was by actually setting very specific values. But there's a problem with both of these models when it comes to doing gradient descent, and they each handle it separately. So in particular, remember that what we were doing is we were calculating a gradient with respect to the weights of the error. And we basically said, not worrying about constants too much, that this was going to correspond to our target value, the correct value, minus, and now here I'm going to make this a little bit more generic than what we saw last time. I'm just going to put a function in here, f of x. And that f of x reflects the output of the network. Now, if we were to have done the derivative off of this form, I'm not done, obviously, because now the next step is I have to apply the chain rule. And then what we found was we were multiplying that times the derivative of that function f. Now, what's important about this is when we were dealing with a purely linear function, which is effectively what Adeline did, then this became, I'll leave it this way, but all we had to do was multiply that times x, because f of x was simply that weighted sum. And we're taking the derivative with respect to one of the members of that sum. The others are all held constant. They all drop out. But the perceptron is using a step function. And so if we're going to try to take the derivative of that step function, Well, we have a problem because we can't take the derivative of a step function because there's that singularity that occurs at the step, that discontinuity. We could try to look at it in a piecewise continuous fashion, but that really isn't going to help us. So instead, it has been suggested that we use a different form of a function. It's a function that approximates the behavior of a step function, and sometimes we'll simply see it referred to as a sigmoid function. So if we were to plot these, the step function is basically saying, and here's our theta, that we're 0 to 1, that we're going to come along, and the function looks something like that. For the sigmoid, I don't know why I wrote a 0 up there. Hold on. Zero to 1. Now the function is going to take a shape that looks more like that. So it is actually a smooth function, and you can control the slope, which basically could get it closer and closer to a step function, but it has the advantage of being a differentiable function. There are a couple different sigmoid functions that we use, but the one that I'm going to focus on today is called the logistic function. And for the logistic function, f of x is equal to 1 over 1 plus e to the minus x. And so what we would be doing for it, in the case of the perceptron is we would be substituting in the output of the network for x. And when you do that, you'll find that it has that sigmoid shape. Well, this then leads to our new derivative of looking like this. Where this is the derivative of the logistic. And so we can use that logistic function as the output function for the perceptron instead of Adeline, and get the type of behavior that we saw with the basic perceptron update rule that we talked about on Monday. I think it was Monday. Maybe it was still Wednesday. So, yeah. So I wanted to make sure that we talked about that because we're in fact going to use the sigmoid functions. The other one that we will encounter is the hyperbolic tangent. But these are going to be two functions that are used quite extensively in neural networks. And I wanted to make sure that we got that introduced. So are there any questions about this before we move into logistic regression? And by the way, we're going to see the logistic function again in logistic regression, which is actually where the name comes from. Okay.
New page.
So let's talk about logistic regression. So I made the comment, I think, at the beginning of the week that in some respects, logistic regression falls somewhere between I'm just going to say the perceptron and naive Bayes. In particular, what we're going to do with the logistic regression is we're going to come up with an alternative way to what we did in naive Bayes to estimate this posterior probability of a class given the input vector x. This is what we want to learn, is learn a model for that probability distribution. All right, so the way we're going to approach this is that, and I'm just going to, for now, simplify the notation and denote that probability P. We'll go back to the more detailed notation in a little bit. So now what we're going to do is we're going to approach this by taking that P, that probability of a class, and we're going to keep it for now in the context of a two-class classification problem, and we're going to compare the probability for that class and the probability of the other class. And you recall that we had done something very similar to this before in defining the Bayes decision rule by taking that ratio and comparing it to 1. Well, if we take the log of this ratio, and by the way, that ratio is also sometimes called the log odds ratio, then this function, the log of the log odds ratio, is, well, that is the log odds ratio. We also sometimes call that the logit function. All right, so what I'm going to do now is I'm going to manipulate this a little bit to see what we can do with it. And to, again, trying to simplify notation here, we're going to just say that y is equal to the logit of p. All right. So I'd like to get rid of that log. It's a natural log. So what we can do is we can take e and raise it to the power of the function. So e to the y. And you'll notice then that gives us our ratio back. Again, a little bit of algebraic manipulation. Let's add 1 to both sides. And we can simplify this down a little bit further. To show that that reduces to 1 over 1 minus p. Now, I'm basically going to just take the reciprocal of both sides, but another way you can think about it is multiply both sides by 1 over p, 1 minus p, and then divide both sides by e to the y plus 1. When we do that, we get 1 over 1 plus e to the y, which is starting to look familiar. It's almost like our logistic function, but it's not quite. So a little bit more manipulation here. Subtract 1 from both sides. And we can multiply through by negative 1. Okay. And again, let's simplify this down. All right. Now, this is actually the form that we are going to use in the context of logistic regression. But notice what happens if I divide both the numerator and the denominator by e to the y. This is actually then equal to the logistic function. In other words, what we just did is we recovered that sigmoid function that we wanted to work with. Okay, but like I say, I'm going to be focusing more on the version that I've circled. Okay, at this point, I need to make an assumption. Let's assume P is Gaussian. Okay, so this is a departure from what we had with naive Bayes, where at least the strict naive Bayes was assuming a multinomial, although we did talk about a Gaussian version of naive Bayes. With what follows, I'm going to skip some of the derivation. The full derivation is in your reading. So I would encourage you to go read the chapter by Tom Mitchell on naive Bayes and logistic regression. But here, with this assumption that P is a Gaussian, we can actually write P. Well, actually, I'm going to go back to the longer notation here. For a two-class problem, we're going to say that the probability that the class is equal to 1 given X can be written using a logistic function. And therefore, the probability of the other class, the class being 0, is 1 minus that. And you find that that then is equal to this. Okay. And as we did with naive Bayes, we will choose the class equal to 1 if this ratio, this inequality of the ratio holds. Now notice that what we've just done is we have represented that odds ratio. And if we take the log of the odds ratio and get the logit, then what we find is that this will reduce to this. So this is really quite interesting because look at what we have right here. This is just a linear function. And what are we trying to learn? We are trying to learn those weights, just like we were doing with both Adeline and the perceptron. So this immediately sets us up for the learning process where I'll tell you, as you'll see in a minute, we can't solve it in closed form, so we're going to apply gradient descent to find those weights. But before I jump into the learning algorithm, I just went through a whole bunch of math, and I want to see if there are any questions. Okay. Well, then let's look at how to learn these weights.
New page.
To do this, keep in mind that what we are effectively doing is we're trying to find a vector of weights that maximizes over the set of possible weights this product. Now, some of the notation here to make sure that we're clear. This expression applies not just to the two-class problem, but to k classes. I'm going to start by solving it for two classes, but different color. K, we're dealing with the number of classes. Well, actually, that's an index into the classes, but oh well. And this is not a power. This is an index, the indexed class. Oops, extra. Oh, fine. All right. So it's still the same posterior probability distribution that we're talking about, the probability of the class given the input, but this time we are also conditioning it on the weight vector as well, recognizing that that distribution is going to change. Change based on the weights that are chosen. All right. So we'll let k equal 2 to get us started. We will come back and I will show you the general multi-class derivation, well, not the full derivation, but the solution there as well. Well, whenever we're dealing with these products, that's usually kind of yucky. So as we've been doing all along today, let's go ahead and take the log. We'll make it the natural log. And then what we're going to do is we're going to define a likelihood function as a function of these weights. And what I'm deriving is a maximum likelihood estimation rule. In other words, I want to find the most likely weights that will enable us to do classification. And we will define that Okay, I see what my notation is now. As this. Now here, we're going to sum over all of the examples in our data set. Actually, let me make that explicit. And because we're only dealing with two classes, let's assume that our class comes from either 0 or 1, where 1 is the positive class, 0 is the negative class. And that way I don't need to fool with the superscript. Oops, hold on. Oh, that's why I use that notation. Okay. So, how do I want to write this? All right, let me explain the notation. So for the first terms in each of these sums, the CI versus 1 minus CI, I'm taking advantage of the fact CI is either 0 or 1. So effectively, for a given example, only one of those two terms will remain because the other one will go to 0. But then inside the probability, I'm assuming that this is just not good. Here, let me rewrite this. Because here what I'm doing is I'm conditioning on the actual state of the class variable. So in the first one, it's the probability that the class is class 1. And in the second term, it's the probability that the class is class 0. Okay, and I think that's a little bit clearer. At least I hope it's a little bit clearer. Okay. I'm going to jump right to the bottom line. There's a bunch of algebra that I could do here, but in the end, what I get is this expression. And let me check something real quick. Yeah, that's right. Okay, so this expression is ugly. And I admit it's ugly. And in fact, solving for W using this has no closed form solution. So this is why we now have to use gradient descent. And when we do that, and again, I'm going to skip all of the derivation, let's just consider the partial derivative of this likelihood function with respect to one of the weights, Wj. Which, to optimize that, we would be setting it equal to 0 and then trying to find what that derivative is. That's where we have to apply gradient descent. The form of this is this. Now that doesn't look so bad, because notice that this looks just like the weight update rule that we had for Adeline, right? And what we're doing is we're summing that over all of the examples in the data set. And I've indexed into the jth feature because it's that feature that is multiplied by the weight that we're taking the derivative with respect to. And then it's just a matter of plugging that into the same weight update equation that we had for Adeline. So it's just the previous weight plus eta times the term inside the sum. Okay, any questions? I'm going to show you pseudocode in a second, which will hopefully demystify a lot of the math notation here. But before I do that, let's see if there's any questions about the math itself. All right, let's look at the pseudocode. So this is the procedure for training logistic regression when you have two classes. So the first thing we're going to do is we're going to initialize our weight vector with random numbers. In this particular case, it's showing random numbers between negative 0.01 and plus 0.01. There's actually good reason for keeping those values close to 0, but not equal to 0, in that if they get too large, when we start dealing with these sigmoid functions, it can lead to what's called node saturation, where we end up pushing the values way out into the tails of that sigmoid, close to 1 and 0, and it's very difficult to recover from that. So this is getting it into a fairly decent part of the weight space to get it started. All right, and then we enter a loop. This outer loop is going to be running through our data and will continue until we have converged, however we're measuring convergence. And that first for loop is initializing the weight updates, where we're just going to go ahead and set them to 0. And then what we'll be doing is we will be adding to those updates as we go. All right, then the second for loop is looping through all of the data. That O equals 0, reflects the output of the logistic regression model. It's a starting point. Then we get to that inner for loop where we're going to be looping over all of the dimensions. It's simply doing that weighted sum. Then we take the result and we're going to pass it through the sigmoid function. Well, what sigmoid function? The logistic function, 1 over 1 plus e to the minus x. We now have an output for our model, and we again loop over all of the dimensions for this example. And what we're doing is we are finding the weight update using the equation that I just showed you. The notation's a little bit different. So just to break that down, we're looking at the jth feature in that loop. R superscript t is the target function. The R is often used to denote a response value, the target response value. And the T, that is referring back to the outer for loop. That is identifying which of the examples that we're dealing with. As you saw, we just calculated y as the output of the sigmoid function. So that is the difference of the target minus the actual multiplied by the input, which was the result of taking the derivative of that linear function. Now notice, since this is all happening inside that for loop, what we're doing is we're setting this up for a batch update. We haven't actually changed any of the weights yet. When we exit that loop where we've considered all of the data, then we have this other for loop where we're going through and we're updating all of the weights by multiplying that sum of adjustments times eta. Oftentimes we might want to do the average first, or we make sure that that eta is small enough that the jumps are not too big. That's the entire algorithm. And in fact, if you relate it back to the way Adeline worked, Adeline followed pretty much the same process. Are there any questions about two-class logistic regression? Okay, well, what do we do if we have more than two classes?
New page.
I'm not going to go through all of as many of the mathematical steps that I did before. I'm basically jumping to the conclusion. So what we have to do is we're going to take our classes, and we've got classes C1, C2 to CK. For J equal 1 to K minus 1, that probability that we were working with, given the input, takes a very familiar form. It's the exponential of that linear function divided by 1 plus the exponential. And then we have to treat the last class a little bit differently so that we're making sure that we get a true probability distribution. And in fact, you can show that it equals this. Which was also what we had when we were dealing with the two-class case. All right, well, this is a little bit messy. So it has actually been suggested and is generally widely used that we want to handle the classes more, the word that the reading says is uniformly, but I want to be careful here because we're not talking about a uniform probability distribution. So not in terms of uniform distribution. So think of it more as treating the classes in the same way. If we do that, then the probability that the class takes on a given value, given x, And this is, well, I'll write that afterward, is equal to the exponential of our linear function. Well, I'm sorry, I left out a term. Oops. I have to go fix something up above, but give me a second and I'll go do that. All right. Now I'm subscripting the, I better do that up here too. J. I'm subscripting the weights to indicate that we have different weight vectors for each of the classes. Now let me go fix those other two equations real quick. There we go. Okay. Now, yeah, sorry I left out that sum, but that's how you normalize over all of the classes. Now, this bottom equation, notice the difference between what's happening there and what's happening in the top version is that we're actually summing over all k classes instead of just over k minus one of them. This results in what we call the softmax function. And it is giving us a true probability distribution. And when we do this, our update equation for gradient descent, you know what? I'm just going to jump to the pseudocode. Looks like this. Okay, so once again, we are summing over all of the classes, recognizing that we have separate weight vectors for each of the classes, and we initialize those weights to small random numbers between negative 0.01 and positive 0.01. The main loop repeats until whatever convergence criteria are met. That first nested for loop is initializing the weight updates to 0, just like we saw before. Then the next set of nested loops, we are looping over all of the data. So we're again going to be doing a batch update. And then the first loop is looping over all of the classes to calculate what the outputs would be for each of the classes. So notice that this is really similar to what you were doing with Winnow, where you had a separate model for each class. That's effectively what we have here too. So this is almost kind of like a one versus all training process. But as we'll see in the end, it isn't, and there's a significant difference here. All right, so we go through, we calculate the outputs for each of our separate linear models in that first inner for loop. And then the next, we are calculating this logistic output by taking e to the o divided by the sum over all of the classes of e to the o. So that's our softmax. And then the last nested for loop within that block is calculating the weight updates using the derivative of the linear function, just like we saw before. So no real change here. And then once we've calculated all of the updates, the final loop goes over all of the classes and all of the vectors and makes the changes. Now, what's different about this compared to what we saw with something like Winnow is that we did not have to explicitly separate the training in the one versus all fashion. We didn't have separate training sets for each class. Rather, this is training them all at once. And it's able to do that because of it trying to calculate this posterior probability distribution directly. So you don't have to play any of the games of deciding, is it going to be one versus all? Is it one versus one? What? You just run through the gradient descent process as shown here, and it will learn those probabilities. You've got the weights, and now you can go back and plug them into the probability equations that we showed you earlier in order to do classification. That's logistic regression. One of the other advantages to logistic regression is even though it's iterative compared to naive Bayes, it still trains pretty fast. And it is often the method of choice when you're first starting to explore a learning method. All right. What questions do you have? I'm not going to have time to prove the perceptron convergence theorem. You can see we only have 3 minutes left. And still feel free to ask questions. On Monday, we are going to look at another linear model, but by the time next week is done, we're going to show how to adapt that model to handle nonlinearly separable problems. And that model is the support vector machine. And I'm not going to make you just sit here for the last 3 minutes. So unless you have questions, I would say we're done. Have a good weekend. Don't forget there is a quiz. The quiz should have already opened, and you should have everything you need to take the quiz.